Okay, class. So for the last two sections that we're going to learn from Chapter 7, we have to sort of switch gears and think more geometrically, because in 7.2 we're finding area of a region, and then in 7.3 we're finding volumes of solids. So that's pretty much the other extremely important application of an integral. We're going to use integrals to do that. So I'll start with sort of a basic formula. So in general, if we're trying to find the area between two curves, we would integrate. And we would first take we'd have to first find the points of intersection. And so you'd have the lower point of intersection as your lower limit, the upper point of intersection as your upper limit. And then inside the integral, you would take the top curve minus the bottom curve. The order of subtraction is extremely important. You have to have the higher curve minus the bottom curve. Okay? So with this generic example right here, it changes. There isn't one set higher curve or lower curve. Sometimes the f function is higher, like for example, between A and C, the f function is higher, but between C and D, the g function is higher. So first of all, we have these 3 points of intersection, which we would have to find unless they were given. Okay, I ran out of room. It's basically points of intersection. So we have those points of intersection, but it switches at point C. Which curve was higher versus lower switches at point C. So to find this, the area of this shaded region, in that generic example there, first we would integrate from A to C. So we take the lower point of intersection up to the higher point of intersection of f minus g for the first part, because f was higher than g was. And then we would add on the integral from C to D of g minus f. And that's how we would find the area of that shaded region. Pretty straightforward. So, and if you think about it, it's just like our formula for finding the area between the curve and the x-axis. But it's just that now we're not stopping necessarily at the x-axis. Like right here, I didn't stop at the x-axis. So instead of subtracting 0, which is what y equals when you're on the y-axis, you're subtracting the actual lower curve, which is, in the first case here, was g of x, and then up here was f of x. Okay, so let's go ahead and apply that to example 1. So I'd like to break this down into a series of steps for you. Okay, so in the first few examples, we're lucky because they've given us the graph. Okay, we're not always going to be given that graph. So what I want you to do in step 1 is to find the points of intersection, because sometimes they won't be spelled out for you. In this case, they are. So we can look and see they're at negative 1, 1, and 1, 1. Because they showed us. But if this wasn't given, then what we would do is basically set each function equal to each other and solve for x. So this is how you find points of intersection, is you set f of x equal to g of x and solve for x. So here's where all that algebra is super necessary, knowing how to solve for x. So because I have x cubed, I can't just like divide x's out. I have to subtract the x over, factor out an x, and then I have a difference of squares right here. So we're going to be doing lots of factoring and stuff like that. So I get, oh wait, I forgot a point of intersection. Whoops, 0, 0. I didn't even notice it right here. So 0, 0. So I notice that I have a point of intersection when x is 0. I have another point of intersection where x is -1, and then another point of intersection where x is 1. And so what happens is that creates some intervals from 0 to -1, and then from -1 to 1. And so I need to figure out for step 2 which function is higher on each interval. Quote, quote, higher. Which one's the top function? So in this case, I could just look at the graph because, again, they gave me the graph. And I can see that from -1 to 0, the f of x function, the x cubed function, is above the line. But from 0 to 1, the line is above the x to the third function. Or you could also do a sign chart. You could go from 0 to -1. Other way around. Duh. You could go from -1 to 0 and then from 0 to 1 and just test a point. So like between -1 and 0, I would test like -1/2. Or excuse me, -1/2. Plug it in here, see which one's higher. Well, -1/2 to the third is -1/8, whereas -1/2 is -1/2. So f of x is higher. -1/8 is not as negative as -1/2. So I can see that f of x is higher from -1 to 0. And similar fashion for this interval, I could test +1/2 and plug it in. I'd get +1/8 and +1/2, and +1/2 is bigger than +1/8. So g of x would be higher from 0 to 1. So then step 3 would be to set up the integrals. And let me emphasize again, the reason I did all this work here is just to show you how you would do this if there was no graph. If there is a graph, you simply look at the graph and go, oh, f of x is higher here, whereas g of x is higher here. So if you're given a graph, use it. Don't waste your time doing all this work. This is just what I would do if I had no graph. Okay, so we're going to set up the integrals. So I'm going to first integrate from -1 to 0, and I'll have f of x go first. So it's x cubed minus x dx. And that'll help me find this area. And then to find that area, I just integrate from 0 to 1. But now the x is greater, so I do x minus x cubed dx. So then for this one here, I just take the antiderivative. So I take the antiderivative, and I have x to the 4th over 4 minus x squared over 2 evaluated from -1 to 0. And so that's going to be basically 0 minus 1/4 minus 1/2. And then I'm going to add that to x squared over 2 minus x to the 4th over 4 evaluated from 0 to 1. So that's going to be equal to 1/2 minus 1/4 minus 0. So the 1/4 minus 1/2 turns out to be -1/4, but it was -1/4. So then this turns out to be +1/4. So that area is +1/4. And then this one here is 1/2 minus 1/4, so that's also +1/4. So I have 1/4 plus 1/4, so the final answer is equal to 1/2. And so that's how we would find the area between these two curves. We found the points of intersection, figured out which function was higher between the points of intersection, and then took the integrals from the lower point of intersection to the higher point of intersection of the top function minus the bottom function. Added those areas up to get our total area. Oh, and with these questions, finding the area of the region, treat it like total area. So notice I did not call this negative. This was considered positive area. So in these questions, when we're finding the area of the region, the areas will be positive. Okay, so let's go on to example 2. So this one's nice. It's given the graph to us. So step 1 is find points of intersection. let's just go ahead and look at the graph. Let's pretend that this really was given to me. I want to show you how simple it can be. I see right away there's just one point of intersection, and it's right here when x is e squared. Okay, because basically it's when e to the x is equal to e squared. Well, the only way that these could be equal is if x equals, x equals 2, excuse me. Right there. So where x equals 2. So the only way e to the x could equal e squared is if x is 2. That's my one point of intersection. But it also, notice it's bounding the curve on the left. And that's what it means by the y-axis. So they're bounding the curve by this curve, e to the x, by the y-axis, which is this guy here, and by the line y equals e squared. So these two intersect where x is 2, and that's the only time they intersect. But we're going to integrate this from 0 to 2 because of the fact that we're cutting it off where x is 2. We're cutting it off right there. So step 2 is to determine which graph is higher. So notice that e squared is greater than e to the x over the whole interval from 0 to 2. So that was easy. And then for step 3, we just take the integral from 0 to 2. And again, that's because it was bounded by the y-axis. That's why the 0 is our lower limit. So it wasn't a point of intersection. It was just bounded by the y-axis. Of the higher graph, which was e squared minus e to the x dx. Okay, so that would equal, so this is just a constant. E to the second is just a constant. So the constant multiple rule just says the antiderivative of that would be e squared x, since it's with respect to x. And then the antiderivative of e to the x is just e to the x. And then we're going to evaluate that from 0 to 2. So then that equals e squared times 2 minus e squared minus 0 minus e to the 0. So this here would just be 2e squared minus e squared. And then this would be negative 1. So it becomes plus 1. So let me just bring this up here. So 2e squared minus 1e squared, that's just e squared, and then plus 1. That would be our final answer. So it's very nice and simple when you have the graph. You don't have to actually work too much stuff out. You just look at it. They intersect right here at 2. E squared was higher the whole entire time. It cut us off right here at the y-axis, so that was my lower bound. So I just integrate from 0 to 2 of the higher one minus the lower one, and then just work out the math. Okay, let's look at example 3. So this one says using a calculator, thank the good Lord. It's always nice when we can use a calculator. So let's go ahead and do that. So if I have my calculator, I'm going to plug in sine x for my first curve. So make sure, again, you're in radian mode, and I am. And then we'll plug in x over 2 for the second function. Whoops. And notice it's just between 0 and pi. So I'm going to make my window match that, because that really helps. Finding points of intersection really helps when you're just looking at the interval from 0 to pi. And when I do that, I like to make my scale for x go by pi over 4s. And I'm going to shrink the y down a little bit, because when you're dealing with trig functions, they never get bigger than 1 or lower than -1. So it's nice to kind of shrink the y min and max a little bit. So here I have it going from -5 to 5. Okay, so there's the sine x function. And then now it's going to graph the x over 2. So I'm going to zoom in even a little more, because I can see there's a point of intersection there and there. But, you know, because it's kind of small, we want to zoom in a little bit. Oops, sorry. So let's first open the x-axis up a little bit. I'm going to go from negative pi over 4 to, I'm going to add another pi over 4 after pi. I'm going to do pi plus pi over 4. Okay, so we're opening that up, and then let's shrink the y down a little bit. Maybe we'll go -3 to 3. But we're only looking between 0 and pi, which would be from here to here. Okay, so there's 2 points of intersection right there. One of them is obviously at 0, 0, and then we're going to find the other one right here. So we're going to do second calc intersect. Y1 is sine, that's it right there. And we want to make sure it's closer to this than it is there. Hit enter. And then y2 is right there, and there's the little cursor mark. So hit enter, and then enter a third time. Okay, now that's a long decimal, and we don't want to round it. No intermediate rounding. So we're going to store this number. So I'm going to go back to the main screen by hitting second, quit. I'm going to store, and I'm going to call this B because it's my second point of intersection. So that's B. Okay, so here's what we're going to write down. For step 1, they intersect at 0 and B, which is 1.895494267. But we have to go all the way to pi. So don't forget that. We're going to find this area right here. And then we're also going to find this area right here. So if you're looking at the graph, the sine x is higher between 0 and b, but the x over 2 is higher between b and pi. So imagine we cut it off like right there at pi. There'd be like kind of a triangular shape right there. And the x over 2 is higher there. So we're going to do the integral from 0 to b of sine minus x over 2, sine x minus x over 2 dx, plus the integral from b to pi, because it told us to go all the way to pi. And on that interval, x over 2 is higher. And we're going to do this all on the calc. So let's go ahead and do that now. So I'm going to do math, FNINT. Where am I? Math, FNINT, and then I'm going to do sine x minus x over 2, comma, 0, comma, and then I'm going to plug in b. That way there's no rounding. So there's, oh dang it, what did I do? Oh, I forgot to tell it with respect to x, sorry. Comma, 0, comma, b. There we go, now it's work. There's our first area, and then we're going to add that to math, FNINT, of the reverse. So now we'll go x over 2 minus sine x, comma x, don't forget that part. And then this is going to go from b to pi. So our final answer is roughly 1.309. Okay, so our final answer is roughly 1.309. And that was adding this part and this part together to give us all the area. Okay, now let's go to example 4. And we're going to, again, find the area of the region bounded by this curve and these 3 lines. So this is really going to help if we sketch the graph, because we kind of want to get an idea of what's going on. So first, let's get solve for y so that we can sort of see it in terms of x. So I could just divide x, so just keep in mind x can't be 0. So I have this curve, y equals 1 over x. I've got this horizontal line, y equals -5, and then 2 vertical lines, x equals e and x equals e cubed. Okay, so let's sketch the graph of that. Well, let's go ahead and graph these lines. Y equals -5 would be like down here. X equals e is between 2 and 3, since e is approximately 2.71. And then e cubed would be between, let's see, it's between 2 and 3, so e cubed would be between 8 and 27. It's kind of a long range, because that's 2 to the 3rd and that's 3 to the 3rd. So it's going to be a big number. We'll just kind of put it over here. It's going to be bigger than e anyways. Okay, and then y equaling 1 over x, this is the graph that goes like this. And it's got the asymptotes at 0 and 0. So there's an asymptote here and an asymptote here. And it's going to go like that. So the area that's bounded by all this stuff, here's the points of intersection that we're going to need to find. And then it's bounded by all of those. So we're kind of looking at this area right here. Actually, we don't need to find these points of intersection because they would be when x is equal to e to the third and when x is equal to e. So for step 1, those are our 2 points of intersection. So I'll write that here. Step 1 intersects at x equals e and e to the third. Then for step 2, we can tell by the sketch that the graph 1 over x is going to be bigger than -5 from these two numbers, e to the third. So 1 over x is greater than -5. And then for step 3, we just set up the integrals. So I'm going to need some room to do that. So I'm going to make myself some room. Okay, so for step 3, we're going to do the integral from e to the third of the graph of 1 over x minus the line -5. So the top curve, which was 1 over x, minus the bottom curve, which was a straight line -5. So that's equal to the integral from e to the third, 1 over x plus 5. And so the antiderivative of that, so the antiderivative of 1 over x is ln of x. The antiderivative of a constant is just the constant times x. And then we'll evaluate that from e to e cubed. So then I'm going to plug in e cubed in there and then plug in e and subtract them. So if I plug in e cubed, I get ln of e cubed plus 5e cubed minus ln of e plus 5e. So that's going to equal 3 plus 5e cubed minus 1 minus 5e. And I super ran out of room again. So let's take this and move it up here since I have some room. So 3 minus 1 is 2 plus 5e cubed minus 5e. I don't know what those numbers are, so I just have to leave them as what they are. And then that would be our final answer. Because I can't combine those. Those aren't like terms. I don't know what they are, so I just leave it. So it's 2 plus 5e cubed minus 5e. Okay, so we just have a few more examples, which we'll finish up in our next video. See you there.